horizon, then you are doing t iterations. And each iteration, you are backing up vk minus 1 to compute vk. In doing that, at each iteration, each of the n states, you have to compute the value function for them. To compute the value function of a state, you have to compute the expected value of doing each of the actions from that state. Right? So, basically, if there are A actions, then you have to do work that is proportional to the number of actions A. And there are n states, so there is n times A work that you have to do for each iteration. And there are t iterations, so you multiply it by t. Now, how many, so basically what we just did is actually t times a times m squared is the complexity, right? And so we are just doing it in polynomial time, which is only squared in the number of states, order of t times a times m squared. In fact, I would have written it as s squared, because we know what s is. S is the number of states. What would be the brute force way of doing it? The brute force way of doing it, essentially, I just said write a big loop for each policy. Compute the value vector, compare the value vectors, and see which is the best. I don't know if you know this, I have this great algorithm for sorting, which is find each permutation and check if it is sorted. Extremely simple algorithm, and I actually came up with it the other day. And clearly it's a brute force dumb algorithm. It shouldn't even be called brute force. It's a brute force dumb algorithm because there are exponential number of permutations. How many permutations are there for n things? Come on, guys. N factorial. Okay, and n factorial is exponential because n factorial by Stirling's formula can be compared to n power n. Okay, to understand sorting and feel impressed about it, you have to come up with a stupid algorithm that I gave you, and then say, wow, n log n is what you guys are able to do. Wow, my God, you guys are smarter than me. You buy like a whole bunch, right? That's how you get impressed by people. So now the question is, TAS square is what I gave you. How impressed should you be at Mr. Bellman, who came up with this idea? Well, if you didn't know about Bellman, you would have just basically done a simple, brute force algorithm, which would have just taken each policy, computed, its value, and then just compared the value functions. So the question, of course, is how many policies are there? Okay. So in each state, you can do A actions. Okay, and there are S states that will give you the size of the policy for one horizon, t equal to 1. Then you have to multiply it by t equal to 2. Multiply it, blah, blah, blah. This is t times. So that means a power s whole power t. Happy life. Right? So you can take this t inside, it will be a power s, t times s. That's what you saved. You went from that to that. That's why you should feel happy about value function. It's not how simple it looks after I tell you the right idea. It is how stupid we would have been if we tried to just do the brute force. Okay? So it's polynomial in the number of states. Now, is that good? Well, it is good if the number of states is very small, but unfortunately, mostly the number of states is exponential in the number of state features or the state variables. So polynomial in the number of states is saying that it's exponential in the number of state variables. But then on the other hand, I said A star is no better. It's also polynomial in the number of states. Okay? Is it better or worse than A star search? I guess I answered the question. Worst case complexity wise, it's no worse. Although it's a much more complex solution concept. Okay. That's the summary of finite horizon. Okay. You essentially are computing the optimal policy pi star such that the Vk to S of pi star is greater than or equal to Vk with respect to any other policy pi. And I did this without actually enumerating all the policies. That's why it is interesting. There are actually those many policies. And I have just given you, by construction, the way to get to the optimal policy. Okay? So what we'll do when we come back next is just make one simple change, which is finite horizon is fine, but in many cases you can actually think in terms of infinite horizon, where you don't know the amount of horizon. It acts as if you have actually infinite number of time steps to live. Okay? And if you have infinite number of time steps to live, what happens? What happens actually is the solution becomes much simpler. Because if you have infinite horizon, infinite number of time steps to live, then you're always talking about V infinity of S. Because you always, even if you lived, as I said, 1 million years, you still have infinite more years to live. Which means actually the policy and the value function are stationary. Are stationary. Do you see what I'm saying? What that means then is actually the total number of policies is much smaller. Total number of policies is only a power S. Actually, it's kind of interesting. Infinite horizon means t equal to infinity, right? So if I just do stupid math, I can put t equal to infinity here, it will be a power S times infinity. That would look like there are infinite number of policies. Right? But the reality is there have to be just one policy. There is no way you can essentially, because in each state you have exactly infinite more steps to live, so there is no difference in value function in terms of the number of steps, because number of steps is always infinite. So actually, when t equal to infinity, you cut this and you actually just go with this, because essentially there is just one stationary policy. So the policy itself looks much simpler. Now, how do I compute it? I can compute it this way. I'll just go with this. Basically, we start with V0, V1, V2, V3. Just infinite number of iterations. I need a bigger slide, but I'll be done. Okay? Now, if there is going to be only one unique value function, you can see even at the completely overheated brains I have right now, that if there is only one unique value function, and if there is any justice in the world, as you keep doing this, the value functions have to converge. Do you see what I'm saying? If you are doing this thing, at some k, some large value of k equal to 200, V200 and V201 will have to be the same value function. At which point you will say, I have found the value function. It's the fixed point of this computation. It's the fixed point of this computation. Okay? That is called the value iteration algorithm for infinite horizon multiplication processes, with one minor but extremely crucial difference, which is that if you have an infinite sequence of states and each of them get a little positive reward, or maybe some positive, some negative reward, what is the total sum of that sequence? Now, do you guys remember the convergence of series? Convergence of series from calculus, right? If you have an infinite series, normally its sum would be infinity. And if your sums are infinity, then everybody is infinity. Infinity makes life basically not very interesting. So the problem with infinity is not so much that it's hard to get, it just makes life much less interesting. That's the interesting way of looking at it. Okay, so you have this infinitely large series and their sums diverge normally. They will become infinitely large. For the kind of ideas that I'm doing, I need to make sure that these sequences converge, otherwise there would not be a unique solution. Now, do any of you remember any series that actually converge? Infinite series. Geometric series. Does geometric series always converge? When will it converge? Ratio factor is less than or equal to 1. Not equal to, and again it will be diverging. As long as, so if you are doing A plus, so if I'm basically doing something like this, if I have A plus A square plus A cube, etc. as the series, as long as the absolute value of A is less than 1, this series has a finite sum. You never thought you would use it in your real life, but that's actually very useful. Okay? So what do? I need to make a normal series which seems to be saying if I'm going through states S1 to S infinity and I'm getting R1, R2, etc. to R infinity. These are all positive numbers. I'm adding them up. I'll get an infinity. I don't want an infinity. I need to somehow convert it into this kind of situation. I'll do the following thing. I'll take, remember rewards are bounded. Every state has at most a maximum reward of, let's say, R max. So what I do is I will consider, if I subtract, I basically take R max out. Then I can essentially get all of these to be less than 1 to begin with. And furthermore, I'll make up a common ratio gamma. In this particular case, I called it beta, which is less than 1. And I say that instead of just adding up R1 plus R2, etc., I will add up R1, beta power 0 R1 plus beta power 1 R2 plus beta power 2 R3 and so on. If I do that, it is actually a power series which will converge. The interesting question is, did I just do looking under the light for my last one? Or is this really reasonable thing to do? I just made a problem solvable by essentially, artificially reducing the rewards of the future, discounting them with respect to current. But is it really that bad? If I were to tell you that you get to either go home right now or over like the entire semester at some point of time, you might get to go home 15 minutes earlier in one class. Which would you prefer?
Right.
By this time, probably most people would have left actually, right? Because you think, who knows, I might drop this class tomorrow. And so why wait until the 10 minutes or 15 minutes Rav is giving at the end of the semester? So you always discount future reward with respect to current reward. Should I give you $10 now or $1,000 when you are 103 years old? Right? Right? And so the interesting thing is we do discount future rewards with respect to current. And so it's not such a bad idea. So it is a mathematical convenience for which we can actually spin a nice story, because that's sort of connected to the way we live life. So we do this discount factor to make infinite horizon modulation process is doable. The moment you have the discount factor, then just doing this infinite number of iterations, as you keep doing it, at some point of time it will reach a fixed point. The value function doesn't change from one iteration to another iteration by more than epsilon, at which point you say, I'm done, this is the value function, you're done. At that point, you can convert the value function to a policy function the way I told you last time. We'll do this whole thing again when we come back.